Hey everybody, welcome back. In today's deck, what we're going to do is explore Coulomb's law, specifically the four most common kinds of problems you're going to see as you do them. So to begin with, a little reminder, 1785, Charles Coulomb comes up with this formula, KQ1, Q2 over R squared, to explain how the force on charges behaves on how much charge they have on them, that's Q, and the distance between them, that's R. What we're going to do is to dive in actually and say something about the letter K. The letter K is what's called an empirical constant of nature. And what that means is that Coulomb, not actually him, others explored the force in detail later when it was possible to objectively measure the amount of charge on objects. And they figured out the value of the K constant. The big thing is they did it by trial and error. That's what empirical means. It's from experience. This thing down here that I've circled, that's a different letter. That's called epsilon naught. And if you look at the formulas and compare them, then you should figure out that this value of K right here is actually equal to 1 over 4 pi epsilon naught. For all the work we're going to do, this is going to be what you use, this guy right here. We're going to use this formula, but I want you to know where it comes from. Epsilon naught is a deep constant of nature. It's one of the fundamental constants of the universe. And what we always do in science is we're not satisfied with an empirical number that works because it works. We always want to know how it fits into the broad architecture of science, and does it hang together with everything else that we know to be true. And it's a further validation of the fact that Coulomb's law is right, that this empirical constant is inside, for example, how light works, which you might not think has anything to do with how static electricity works. But that's what we like to do in science. We believe in the way science works because it's deeply connected one thing to another thing, and all of them are testable, every single step along the line. Okay, so having said that, brief little review, or if it's the first time you're seeing it, that's fine too, about unit vectors. We're going to use unit vectors a lot, and there'll be another deck in just a little while that you're going to look at if you want to, that's going to teach you everything you need to know about unit vectors. But the reason they're useful is that they save us from having to deal with vectors at angles, which is often annoying. What I just drew was this, a vector pointing to the right in the positive x direction. We're going to call that the I direction, which is not tricky. If I drew a vector arrow pointing back that way, that would be the minus I direction. You guessed it. And so up and down work the same way. So up is going to be called the positive J direction. And you notice that what I'm doing is I'm drawing a hat on top of the letters. And that's standard, that's traditional. The J hat indicates that it's a vector. So up and down, J and minus J, okay? And the K and negative K directions for in and out of the paper work exactly the same way, okay? So just a mention of it, you'll see it used a little bit in the deck that you're gonna go through right now. Okay, so first problem, what we've got is a 10 microcoulomb sitting 15 centimeters to the left of a 1 microcoulomb test charge. So here's my advice. I really don't get bent out of shape about minus signs. I use them in a way that I think is appropriate. Big thing I always urge my students to do is do a simple diagram. I know this is a simple question, but do a simple diagram. I've got a 10 microcoulomb test charge sitting there, and that is 15 centimeters away from a 1 microcoulomb test charge. I know that the force between these is going to be repulsive. They're asking us for the magnitude and direction of the force exerted on this one, the test charge. If I just look at it and use my common sense, I don't need pluses and minuses to tell me the shove is going to be this way. This guy's going to be pushed to the right. And when they ask me for the magnitude and direction, the answer for the direction is it's going to be the I direction. Okay? So we're just going to get right down to it then. Force equals K, Q1, Q2. Oops, Q1, Q2. And I think I switched to uppercase over here. And I'll say something about the way I draw these or write these out. You can write 9 times 10 to the 9 Newton meters squared over Coulomb squared. That's good practice. You can write 10 times 10 to the negative 6 coulombs. That's good practice. You can write 1 times 10 to the minus 6 coulombs. That's also good practice. You can write 15 times 10 to the minus 2 meters and square it. and that's all good practice. I would be just as at peace with this. As long as you promise that you really understand the metric system and you recognize that whenever you see two letters, you realize that the first letter is a metric prefix, the only exception being kilograms, because kilograms is a standard label, but all the standard labels in physics except kilograms are single letters. So whenever you see a letter that's a prefix, you can write, if you wanted to, if you found it easier in your writing, if you wanted to write 10 microcoulombs and just write it down like that, that's fine. 1 microcoulombs, people do that all the time. Adults write that way. But they also know that they don't blow through those metric prefixes. When it's time to reach for the calculator, this right here, the thing I wrote out longhand, that is what you're typing in. Okay, so I'm going to make sure we're clear on that. When you plug all this stuff into your calculator and you square the distance, of course, you're going to end up with 4 newtons. Go ahead and pause the deck. Check me out and see if you agree. Okay? So next slide. 1 microcoulomb test charge is placed some distance to the right. All right, so what we've got now is negative 15 microcoulombs, and that's my little test charge, right? Not my test charge, it's my big charge. 1 microcoulomb is out here. And you notice that one of them minus, one of them's plus. What I'm doing right now is formulating in my mind how the answer is going to come out. They're going to tell us some other stuff about how the force acts. I know that the force, just by looking at these, is going to be in the negative I direction. And then that matches up with what they tell us about the force. The thing I wanted to say about this is that personally, I never plug minus signs into formulas like Coulomb's law. I strictly deal with the magnitudes of things because I realize that the minus signs are there to indicate direction down the road. So I set them aside. And I have seen many times students kind of robotically plug in the number that they're given. They plug in a minus sign, and then they end up saying something silly about which way the force is pulling or how it acts. So what I'm going to do is just dive into the algebra, and I'll show you what we're doing with this one. F equals KQ1 Q2 over R squared. And we're going to solve this one for the distance. So that means just we're swapping algebraically KQ1 Q2 over force, and then we'll take the square root of both sides, and what we end up with is the R equals the square root of K, and let's see if it can be a little more legible this time, K1 Q2 over force. And here's what I was saying about the metric prefixes. I'm okay. If you want to write down K and just write it as K, that's fine. Q1, I never write minuses. There's no point. 15 microcoulombs, 1 microcoulomb. Just make me a promise, and that is that you know what those micros stand for and you use them. And then the force is 10 newtons. And when we work this out, we're going to crank it through the calculator. We get 0.116 meters. So that would be the same thing as 11.6 centimeters, I believe. Okay, so there you go. Third type of question. What we've got is 2 identical charges placed a distance 50 centimeters apart, and they give us the force acting between them. Okay, so here's a good example of the metric prefixes. So newtons is a standard unit. The fact that I see a big M in front of it means this is trying to tell me something about the power. So this is going to be a meganewton, 1 times 10 to the 6 newtons. So that's a big force. That's like 1,000 tons of force between these two things. So the charges are probably huge, right? 1,000 tons of force. So 2 identical charges, Q1 and Q2. Let's do ourselves a favor. If they're identical, let's just call them Q, huh? And I've got a force acting 50 centimeters apart. Let's just get into the formula for it. We've got force equals K. If this is Q and that is Q, really, I guess I could just write force equals KQ squared, right? Over R squared is my force formula. And now we're going to try to solve this thing for the value of the charge. We'll do our algebra, and we get Q squared equals FR squared over K. And we'll again do the square root thing. So Q is equal to the square root of FR squared over K. And we'll plug that in. So let's go see what we got. F is 1 times 10 to the 6 newtons. K, we'll put down the bottom. I meant to jump to R next, but I didn't. 50 centimeters, so 0.5 meters. And don't forget to square it ever. And divided by K. And so we go ahead and do this, and we were saying the charge is probably huge, right? Now, the value of the Coulomb constant K is so huge because electrostatic forces are really, really strong. One of the strongest forces in all the universe, which really makes how atoms work fascinating when you get this. That the force between charged objects is humongous. So what do we get? That this is a tiny amount of charge, 0.0053 coulombs, or Q is equal to 5.3 millicoulombs, very small. So again, electrostatic force is humongous. Finally, really common kind of question. This is like an SAT question posed as a physics question almost. Two charges are placed 10 centimeters apart, and they generate a repulsive force of 400 newtons. It doesn't even matter if these charges are identical or not. What I'm going to do is go right to the Coulomb law. So K Q1 Q2 over R squared. The thing that you want to notice is that these Q's are to the first power. The R is to the second power. So when the charges on each one are halved, that means they're cut in two. Every time you do that, you cut the force in half because the relationship between Q and F is that they're both to the first power. So the answer to A is that I cut both in two. What's going to end up happening is the force becomes 1/4 of the value that it had before. Okay? So a little bit different is that the way the distance affects the force is that the distance is to the second power. So for example, if I were to double the R, the force would drop, and the force would drop by a factor of 4 because I would be squaring that factor of 2 that I had done down here. So when force is proportional to 1 over R squared, all we do is we put in the factor, and in this case the force is going to change by a factor of 1 over 4 because we're quadrupling the distance, but we have to square it. So the force will be 1/16 as much, and what that does is it tells me that the force will become 400 newtons over 16, which is 400 newtons divided by 4, and then divided by 4 again, and I think that's 25 newtons. Okay, and there you go. 4 most common kinds of questions. Bring your questions to class. Take care, and thanks. Bye-bye.